This week on the Magic School Bus.
Are you kids ready to learn about Bhutan today?
But Miss Frizzle, we don't want to learn about Bhutan. We want to learn about large-scale nano-manufacturing.
You kids are much too young to learn about that.
No, we're not. We've read books and stuff about it.
If you've read books about it, what do you know about it?
I read that nano-manufacturing can be described as large-scale production of materials that derive qualities based on its nanoscale dimensions, and that being able to manufacture these nanomaterials will allow technologies in energy, medicine, and cosmetics to advance in ways bulk materials wouldn't be able to. Nanomaterials can be synthesized through top-down methods such as nanolithography and bottom-up methods like self-assembly.
If you've read all of that, you must have also read that an enormous amount of nanomaterials need to be produced for intended applications. Overall yields are paltry for long multi-step processes, even with a yield of 99% in each process step. Heat and mass transport behavior of nanoscale processing impacts product uniformity and homogeneity. As a result, large-scale nano-manufacturing is simply too expensive and impractical to execute.
But Miss Frizzle, what about all the possibilities out there?
Please, we'd love to learn about it.
Nano-manufacturing is very unique because it's the fabrication of macroscopic products through well-defined nanoscale building blocks, which is something that man-made manufacturing processes have yet to perfect in a large-scale setting, for the reasons I mentioned earlier. To make large-scale nano-manufacturing a reality, there are design considerations that would have to be made specifically for the nanoscale. Aside from economic and performance considerations, there are several integral nano-manufacturing process design needs that should be considered while finding the best process. These include appropriately selecting process breakpoints in iterative assembly sequence, synthesis techniques that are appropriate for scaled-up manufacturing, new structure and property-based separations, and finally, advances in stabilization and packaging.
Wow, that's a lot of considerations.
It really is. Well, to learn more about it, let's visit some different labs to learn about what processes are currently in practice and what researchers are doing to move them in the large-scale direction. First off on our field trip is to learn about how chemical vapor deposition is used in nanofabrication.
I learned all about that from a cool book I got in the library.
If you want to learn about nanomanufacturing, we're going to have to shrink all the way down to the nanoscale.
Chemical vapor deposition, or CVD, is a basic tool of manufacturing. It is used in everything from sunglasses to potato chip bags and is fundamental to the production of much of today's electronics. Here's how the process works. The CVD process begins with tanks containing an initiator, red, and one or more monomers, purple and blue, which are the building blocks of the desired polymer coating. These materials are vaporized either by heating them or reducing the air pressure, and are then introduced into a vacuum chamber containing the material to be coated. The initiator helps speed up the process in which the monomers link up in chains to form polymers on the surface of the substrate material. The hot gaseous material naturally forms a coating on the colder substrate, much as water vapor coats the outside of a cold drinking glass on a hot day.
Very good. I can see you spend a lot of time in the library. Maybe consider playing outside a little more.
Miss Frizzle, I want to learn more about large-scale nano-manufacturing.
Time to go to another lab to learn about nano-imprint lithography.
Hey, I watched a documentary about this. Nano-imprint lithography is a simple process that uses a mold, which is a mask used to transfer a desired pattern, to emboss a resist, which is the material that receives the pattern. Particularly in thermal nano-imprint lithography, a thin film is pressed and heated between a pattern template and a substrate. Upon heating, the pattern film adheres only to the substrate. After embossing the resist, the compressed resist material is removed using anisotropic etching, and the substrate is exposed.
Really impressive. I'm beginning to wonder if you kids know more than I do. Well, let's move on to the next lab to learn more about Langmuir Blodgett films.
No way, those are my favorite.
blodgett films, or LB films, are a class of thin films that utilize bifunctional molecules to coat a substrate. The molecules usually contain a hydrophobic and hydrophilic end group similar to phospholipids. The first step in forming LB films involves dispersing the bifunctional molecules across the liquid-air interface of a trough. The molecules can be packed together using a movable barrier. The next step involves submerging or withdrawing a substrate from the trough. This causes the film to adhere to it. Depending on the substrate and the solvent, the orientation of the molecules can be changed. This process can be repeated to add additional layers on top of existing ones. Because the molecules are added homogeneously, the thickness of the films can be tailored by altering the size of the molecules. This allows for extremely precise control of film thickness. LB films are of great interest to many fields because it is easy to adjust the properties of the film, either by changing the molecules or by adjusting the molecular orientation. The ability to adjust molecular structure is of special interest because adjusting the molecular orientation alters the material properties in ways not seen in bulk materials. Possible applications include passivation layers, lubrication layers, and others. Unfortunately, LB films will not see full-scale production for many years. Current problems include how to properly repair damaged films. Additionally, many scientists are skeptical of the properties observed in some papers. Despite the complications, LB films remain an area of intense research that many scientists hope will prove worthwhile.
Once again, student has become the teacher. Maybe you guys should be getting my paycheck. Well, we only have time to learn about one more nano-manufacturing method on this field trip.
Please let it be self-assembly. Please let it be self-assembly.
Learn about self-assembly.
Yes, I listen to the best podcasts about this.
Self-assembly is a bottom-up process in which a group of nanocomponents, such as structures and patterns, spontaneously come together from basic building blocks to form an ordered structure without outside influence. Self-assembly is present all throughout nature, exemplified by living organisms and galaxies alike. Unfortunately, researchers are still learning to mimic these processes to apply them to nanomanufacturing. There are a few major controls on the self-assembly process that add to the challenges, including the molecular shape, enthalpy, entropy, molecular weight, composition, and interaction parameter. A general method of directed self-assembly that is thought to be a possible solution to the large-scale nanomanufacturing problem uses nanotemplates. Nanotemplates can be used to enable precise assembly and orientation of several nanoelements. An example of this is demonstrated through template-assisted electrophoretic deposition. The assembly process can be controlled by altering the applied voltage, assembly time, and/or the geometric design of the templates. These controls can produce monolayers or multilayers, as well as full or partial nanoparticle assemblies. This approach presents the possibility of an effective and efficient means of nanoscale directed self-assembly over a large production scale. Polymer melts of block copolymers are often used in self-assembly applications because they are able to self-assemble into many different morphologies. This allows for flexible templates for nano-device assembly. Using nanotemplates to control these morphologies in high-volume manufacturing methods could enable commercial production of nanoscale morphology and polymeric materials. Although it is difficult to ensure perfect patterning, self-assembly has fair potential to help actualize the goal of commercially scalable nanomanufacturing. It could enable development of complex, functional structures, have high reproducibility, and potentially be inexpensive. Using this natural process of building from the bottom up, nanocrystal by nanocrystal, is thought to be more efficient than other methods available in a lab setting.
Seems like you guys know everything there is to know about nanomanufacturing now, don't you?
Well, actually, what is the future of it, Miss Frizzle? Where will all of this take us?
I would never ask. There are still significant barriers to implementing nanomanufacturing on an industrial level. The precision of methods required for laboratory research are often impossible to translate to large-scale manufacturing, due to heat and mass transfer being difficult to control, which reduces project uniformity. As a result, extra steps must be taken to isolate desired and undesired components. However, millions of dollars of research are being poured into the subject because of the huge payoff if the process is perfected.
This program was made possible by the Corporation for Nano Broadcasting and viewers like you.